Okay, we're at the point now where we can put some of this together and come up with kind of the main question type we're trying to answer when we're talking about equilibrium concentrations. And what we need to be able to do is look at an equilibrium system and then be able to figure out if I put a certain amount of chemical into the flask as initial concentration. So let's just use this one here. So if I have my flask, and of course my flask has to be sealed so that nothing gets in and gets out. If I put initially a certain concentration of A and B in here, whatever those two chemicals happen to be, we know as they reach equilibrium, they're going to produce some C and D. So if this was the initial flask, so we're just starting out, the final flask we know would then contain all four chemicals because the reaction would have proceeded until we got the forward and reverse reaction rates to be equal. And then what we would find in here would be some new concentration of A, some new concentration of B, because we don't use them all up. It's an equilibrium reaction, so we don't go to completion. There would be some C having been made and some D having been made. Right? So all of the things will be present at equilibrium. So at equilibrium, the trick is how do we know how much A and B were used up and how much C and D were produced? So that's the question we want to try and answer to get from this initial concentrations to these equilibrium concentrations. Okay? So there's two things you need if you're going to be able to do this. The first one is, of course, the KEQ. So these are questions where you're going to be given or have some way of getting the KEQ. And you'll notice in all of these questions, they occur at a constant temperature because you need to keep the temperature constant so that this KEQ remains constant. So if you change the temperature, then you no longer can solve these questions. So the first thing we're given is the equilibrium constant. And the next thing we'll be asked to do then is based on some initial concentrations, we will be asked to find the concentrations of all the entities that are in that chemical equation. So we're going to use some stoichiometry. So you'll remember some of that from grade 11. The molar ratios that are in the balanced chemical equation can be used in combination with this K value in order to solve for how many of each of the reactants and products is there at equilibrium. Okay, that's a lot to go through, and probably the easiest way to do it is just to take a look at a question to see how we move from here over to here. Okay, so let's take a look at one. This question deals with hydrogen iodide. So hydrogen iodide is a clear, colorless gas. This is colorless if you were to be looking at it, and we did this in the actual lab. And of course, we've got hydrogen and iodine here as reactants. Well, hydrogen, you know, is colorless. So there's actually a color here that makes us able to see what's going on. This is actually iodine gas, which we've seen in class before is purple. So we're going to see macroscopically, visually, we're going to see a purple color. And as it moves toward products, it's going to become more and more colorless. So we should, if we were watching this in an actual beaker, we'd be able to see that purple color slowly go away if it was shifting toward the products. Or if it was shifting toward the reactants, we would see that purple color get darker and darker. Now, if we look at our question, we see that we're given only the reactants in this question. So that means if you're only given the reactants, the shift that's going to occur in this question is going to be to the right. So we would notice our equilibrium system becoming less and less colored. The purple color would be decreasing. And eventually, if it went all the way to completion, the flask would become completely colorless. But we know that's not going to happen because this is an equilibrium system. But if we take a look at the K value here, it's got a fairly large K value. 49.70 is quite large. So that means that a large K value means we're going to have mostly products at equilibrium. So this flask should be very lightly colored when it's done because of this 50, almost 50 for an equilibrium constant. Almost all of the reactants should be turned into products when this thing reaches a balance point. And that's given by this large K value If the K value had been small, then we would have expected the equation to remain purple, because a small K value means you have mostly reactants left at equilibrium. Anyway, let's have a look at this. We have 2 moles of each reactant is initially put in a 1 liter sealed flask, and we need to calculate out what's going on. So let's set the question up. The easiest way to do that is with an ice table. So we've got our table here that we can work from. If you recall, then ice tables, we put down, first of all, the initial concentrations. Well, we know that this was a 1 liter flask, and we know we were given 2 moles of each of these things. So this is 2 moles and 2 moles. If they're in a 1 liter flask, then the initial concentration of H2 would just be 2 moles per liter. And I2 would be the same thing. I2 would be 2 moles per liter. Now I'll go back to the original question here. How many significant digits do they have, so we can have that in our answer? You'll notice that our original here had 3 significant digits, so keep that in mind when we go to write our final answer. And I should be putting that here on my data table. I'm getting lazy, I guess. And then HI, well, because initially there was no HI in the equation, in the flask, this is going to be 0 moles per liter, okay? And our equation is right here. I just like to put this in so I can remember which things are products and which things are reactants, okay? Now, we said when we looked at the question that this thing is going to be shifting, and it's shifting in this direction. So what that means for the next layer of our ice table is we know how things are going to be changing. We know we're going to be using up some of the H2, and we're going to be using up some of the I2. So those changes in those 2 concentrations are going to be negatives. They're going to be used up as this thing shifts to more products. And that means then on the product side, this is going to be a positive change, whatever that change happens to be. Now, since we're going to look at stoichiometry, we can just assign the change in concentration to a variable. So I'm just going to say, because H2 is going to change a certain amount, I'm going to say that it changes by an amount called negative X. So we don't know what that amount is. We know it's going to be negative. Let's just label that negative X. And then with stoichiometry, since this is a 1-to-1 relationship, H2 to I2, then this would also change by negative X, because whatever happens to the H2 has to happen to the I2. It's a 1-to-1 relationship. Okay. Now on the other side, we see that we've got a 1-to-2 relationship. So since I made negative X for the H2, well, I'm going to make it a positive change on the product side. And because it's 2 HIs, its coefficient, I'm going to make this 2X. And so that's how we can establish what the change in concentrations would be without actually knowing how big the change is or what the equilibrium concentrations are. We simply assign one of the changes, the variable X, and then use stoichiometry to be able to figure out all of the other changes, because this thing has to react according to the balanced chemical equation. Okay, so I put the 1X here for the H2, made it a negative. This is 1-to-1, so that's also a negative X. And then this is 1-to-2. So, and we're crossing the sign, or the formation sign, so we're going to make that a positive, and it becomes positive 2X. So now the other thing we needed to be able to solve this equation, we're trying to find equilibrium concentrations. So we can come down here and get our final row of E. Well, we just add these columns up. So this just becomes 2 minus X. This becomes 2 minus X. And 0 plus 2X just becomes 2X. And so that's the chemistry behind setting up an equilibrium question. Now the equilibrium concentrations of each of our things are described in terms of a variable, but are now possible to be solved for. So we've got 2 minus X, that'll be our concentration of H2. That makes sense. It started out at 2, it's going to go down by a certain amount called X. I2 is going to go down by x as well, and then we're going to make 2x of the product. Okay, so the next step here is to take this equation. So remember we've got, I'm just going to bring that down so we can continue to see it. Take our equation, we can write an equilibrium law for this. So if we were to write that out, what we'd end up with, grab a pen, sorry, let me grab a pen. We would say that our K EQ for this particular reaction is equal to, well, it's the products over the reactants, HI squared all over H2 times I2. So that's our equilibrium law expression, the products over the reactants. But now we can actually fill this in. We've got some numbers here. We know that the KEQ is the ratio of reactants and products at equilibrium. So we can use these equilibrium values and put them into our equation. So what we have here then is, since HI was 2x, it then becomes 2x squared, just subbing in from my concentration of HI. H2 was 2 minus x, so we go 2 minus x. And the I2 was also 2 minus x. So all we've done is taken the equilibrium expressions here that we created using the changes in the concentrations, and we plug those in as our equilibrium values. Now we still don't know what it is. We've got an x that we need to solve for, but we've got one variable inside this equation, but then we need to set it equal to something. Well, I haven't got it on this screen. We'll go back. There's the number right there, 49.70. So we can set this all equal to 49.70. And that's where the chemistry kind of stops and the math begins. And so now you've got the task of solving this equation to be able to solve for x. Once we get x, we're going to take it back up here, and 2 minus x will be our equilibrium value, or 2 times x will be our equilibrium value. But we need to solve for x. We need to rearrange this and solve it in such a way that we get a value for x. Now this one isn't too bad. Some of them will get into the fact that you'll need quadratic equation. But in this one, I think we can get an easy out on this one, because if we take a look at it, we realize that 49.70 is equal to 4x squared over, now you could FOIL these out and figure out everything there, but if you see this, you'll notice that it's actually 2 minus x squared. And this will let us jump out of this question just a little bit easier. If you went and expanded everything out, you'd end up using quadratic equation to solve for x. But if you see this here, what we can do now is, because that's a squared term and that's a squared term, what we can do then is take the square root of both sides. So if we take the square root of 49.7 and we take the square root of this side, well, the square root of this side would just be 2x over 2 minus x. So I'm just taking the square root of that whole side, taking the square root of both sides. So I'll just put that over here. Take square root of both sides. Okay, then we get this. Now we can simply go through and solve that. We've got something that's just got some x's in it. We've lost the squared terms. And now it's just a matter of doing some rearranging and solving it. So let's do that. Let's do the rearrangement. Probably the first step most of you will take is you'll first figure out the square root of 49.7. And the square root of 49.7 is 7.05. I'm just rounding off to make it easier to write out. 7.05 equals, and I'm going to do this one out in detail. Some of our algebra skills are not always the best. So we'll just go this first one out, but you can solve these however you want. It's going to depend on the strength of your algebraic skills. Okay, so that's what we've got so far. And then what we're going to do is we're going to multiply both sides by 2 minus x. So we can get rid of this term on the bottom. So that means we get 14.5 7.1. That's 2 times 7.05. And then we get minus 7.05x equals 2x. We simplify that again. We just collect up all our x's. So I'm going to add 7.05x to both sides, 7.05x to both sides. So that gets me 14.1 plus 9.5x, sorry, 9.05x. And then x would be found by dividing both sides by 9.05. So we divide both sides by 9.05. And we end up with 1.56. So 1.56 is what we end up with for our value of x. Okay, so we go back up to the top here and just take that 1.56 with us, and we take a look at our answers here. So I'm going to go all the way back up here, and you can double check here. So if x is going to be equal to 1.56, let's make sure that makes sense. So 2 minus x, yeah, that'll still be a positive number. It'll be 0.44, and then 2 times x. So all of those, we need to go back and make sure that when we put in the x, we can actually evaluate it and get a number that makes sense. You can't have a negative equilibrium concentration. So if for some reason 2 minus x came out to be a negative value, you need to go back and look at your math because you've made a mistake somewhere. Equilibrium values should never come out to be negatives. Okay? So, but we see that it's not. 2 minus x evaluates out to be 0.44 moles per liter. 0.44 moles per liter. And then finally 2 times x would be 3.12 moles per liter. Okay? So that is how you solve those. Now, if you didn't see the perfect square, I think it's called perfect, whatever, you didn't see this square down here that you could take the square root of both sides, then your next line here would have been just to evaluate this, and you'll get it into the form ax squared plus bx plus c equals 0. You want to get it into the form for a quadratic equation, and then you can, you don't need to show me how you get that. You can use your calculator, you can use an online app. Somehow you want to solve for the roots. So you would solve your rearrangement to get the 2 values for x, right? You'll get the solve for the roots, you'll get 2 values. And often one of those values will always drop out. And often what it is when you get your 2 x values, one of them will be, well, one of them would be positive 1.56. I'm not sure what the other one is. I haven't done it out using roots. But the other one, you'll be able to throw the other root away. It just won't make any sense. Sometimes x just comes out to be too big, so that 2 minus, if it's x is bigger than 2, then that's not right. It can't happen. Or if x is a negative, you can't have a negative change. The way we're setting this up, the value of x has to be a positive because we're putting a negative in here. So the value of x has to be a positive. You can't have a negative coming out for an x. So you could rule that out either by looking at the equation or by realizing that the negative can't be used. And so that gives you the one to use. So you can certainly use quadratic equation, and that would just pop in here instead of going through and realizing you can take the square root of both sides, because some people just won't see that. Okay, so that's how you answer those questions. And then we're trying to get it here are these equilibrium values in moles per liter for each of the things. So that took a little bit to work through. I will leave this video at that point, and I will endeavor to post answers to the remaining 2 questions. So if you look online, you'll find lecture sheet number 3, I think, question sheet. And it's got this question about carbon monoxide and this question about, what's this one about? Oh yeah, nitrogen monoxide and chlorine gas. Okay, so those two questions, I will put up answers as we proceed. You'll also find on that lecture sheet a set of steps that I just went through. And so these are the steps that I suggest you follow as you try and do these questions. But the next one follows the same pattern as what we just did. So try and set it up in the same way and see if you can at least get the ice table filled in, write the equilibrium law expression, and then if you get stuck, come back and we'll work through the math of simplifying it down to get an x value together. Okay, so I'll leave it there for now and come back with a couple other videos on the other two questions.